All right, find the equation of motion. Okay, find the equation of motion. So what is the equation of motion here? The question asks you to find the equation of motion, EOM, right? So of the uniform rigid bar OA of length L and mass M shown in this figure, also find its natural frequency. So you have to find two stuff here. First, the EOM and also the natural frequency. Okay, so what is EOM? So I'm going to go here. Is it this one? Wait. This was supposed to be the EOM. It's in the lecture 4. Nope, not here. Wait, Okay. Okay, this is your EOM. Okay, EOM is in the you can solve questions if the question asks for EOM using X or using theta. Okay, depends. Same thing basically. So EOM can be either in X double dot plus omega n squared X equal to 0, or theta double dot plus omega n squared theta equals to 0. Same thing, you'll get the same answer for omega n. But if question asks only for UM, then you can just solve your equation to be in this form. Okay, if the question asks for UMN omega n, solve your solution to get this form first. Okay, to get this your answer to get this form of UM first, and then you can further calculate to find your omega n from this UM also. Okay, so let's try and do this. Okay, first of all, you can, if the system given in the figure, you can see whether it's moving translational or moving rotational. If they are using both, for example, if like this, right? Like this, there's two motion. You can find rotational for the, what is this? The cylinder, right? You can find a rotational motion in the cylinder, and also translational for the springs, right? There's two motion here, so you can either calculate your answer in X, or you can choose to calculate your answer in theta. But for this question, there's no what to call that, two motions. There's just one motion here, which is rotational. So you can only use rotational for the whole calculation. So first of all, try to do a free body diagram, like a schematic diagram like that, first before solving for your EOM. Okay, I'm just going to show it over here. Okay, the blue line is the original position for the bar. The red line is the new position of the bar after it rotates clockwise. Okay, this is the rotation here, clockwise rotation. Okay, and this is your A. This is your this is the radius, because O is the pivot point, right? O is the pivot point. So A is the distance from the pivot point to K1. That's A. L over 2 is the distance from the pivot point to the center of gravity. Okay. L is the distance between the pivot point and K2. Okay. So imagine if the spring, okay, if the spring here, from the original position of the bar, the blue line, to the red line, right, the bar rotates clockwise. Okay, so for K1, is attached to the bar originally. Okay, not originally, the K1 is attached to the bar. And then when the bar moves downward, right, when the bar moves downward, what happened to the force, to the spring force in K1? What is the direction K1 moves when the bar moves downward? If the bar moves downward, the force, the spring force for K1, all right, it will move upwards to counteract the bar moves downward. Basically, the K1 is attached to this, let's say, a wall, right? Let's say a wall here. K1 is attached to a wall here. So K1 cannot move. Okay, and when the spring is pulled downward, there's this spring force that counteracts, that pushes the spring to the original position. Okay, which the resultant force will be, sorry, moving, pushing upwards, okay, to the original position. And for K2, same thing happened. K2 is attached to wall here, okay, and K2 is attached to the bar at the position A, right, at the original position. And when the bar moves downward, basically it compressed K2. Okay, K2 is being compressed here. When K2 is being compressed, when the bar moves downward, the resultant force from the spring will pushes the bar upwards, okay, to the original position. So it will look like this. This is K2. All right, wait. Okay. Wait, it's getting messy here. I'm going to move the picture. Okay then. K1 settle, K2 settle. Oh yeah, KT. Okay, KT is torsional spring. Okay, torsional stiffness is KT. So if the bar moves downward, all right, let's say what that clockwise. Okay, the bar is moving clockwise direction. So what will happen to KT? In what direction KT pulls the bar back to the original position? Okay, so basically KT pushes the bar pushes KT when the bar moves downward. The bar pushes KT in this direction, right? So the KT will pushes the bar back to the original position in this direction. Okay. So I'm gonna put it over here so you guys can see. This is KT. Alright. So basically KT pushes the bar back to the original position in the opposite direction that the bar is moving. So I already complete my schematic, and then I'm going to take out all the forces in this diagram. So for K spring force, okay, equals to F equals to Kx, right? Show one by one here. F equals to Kx. And then F equals to K. Our K is now is K1, right? Our X now, X is basically the what to call that, the displacement for the spring, right? So what is the displacement for the spring? This is the displacement for the spring, right? It moves, it's like a part of a circle. Okay, the bar moves like this. So what is this displacement here? Okay, remember, x equals to r theta, right? So the displacement for K1, okay, the displacement for K1, the x will be r theta, but the r of K1 is a. R is the distance of the force from the pivot point. So for K1, the distance from the pivot point is a. So our x will be r theta, our r will be a theta. Right, so substitute here a theta. So this is the force for K1. Now let's do for the force for K2. Still F equals to Kx. Our K now is K2. Our x equals to r theta. So what is the displacement here? X equals to r theta. So our r, the distance of K2 from the pivot point is L. So L theta. And lastly, for KT, wait, F equals to Kx. And then F, our K now is KT. Our X is theta because there's the displacement happens in rotational motion, right? So there's no x equals to r theta here. There's no radius here because it happens at the pivot point. Okay, it's straight away coming from the pivot point. So the only displacement here is in terms of theta. So F equals to Kx is equals to F equals to Kt theta. So these are the forces from 3 different types of springs. Now, the bar itself is moving clockwise. So the first thing that we need to know is to find the m naught. So you have to define your m naught moves in what direction. But typically, we'll just assume the moment, okay, to be in the same direction as the system goes. So the bar now moves in clockwise motion. So our moment will be positive in clockwise motion. So m naught equals to j naught theta double dot. Wait, I think I see it somewhere here. Also in your slide, but this one is lecture 4. Wait, yeah, here. So moment, summation of moment equals to j naught theta double dot. So use that. Before that, so basically our m naught is j naught theta double dot. Our j naught theta double dot is the moment. So what is our moment here? Our moment here, we have 3 different types of forces. All right, the 3 different types of forces. The first force is, I'm going to use the kt here, kt theta. This is the force. Remember, moment equals to force times the distance, right? Moment equals to force times distance. So this is our force now, kt theta. So our distance is, there's no distance because this is already in theta at the pivot point. No distance here. So we can just put as kt theta. But remember, we define our position to be clockwise. Since kt is not clockwise, kt is anti-clockwise, so it is negative. All right, negative. And then we go to the second one, K1. The force is K1 A naught, right? But then for moment, the force, which is K1 A naught, for example, right? K1 A naught, then you have to multiply another distance, the distance from the pivot point. So K1 to the pivot point is also A, so you have to multiply another A. Okay, this is force. and this is distance from the pivot point. So force times, so basically that is the direction. So for K1, it is moving upwards, right? So since it is moving upwards from the pivot point, it will be like this. So it will be in anti-clockwise direction also. So it will also be negative. Negative what? Negative force times distance. The force is K1A theta times the distance A. All right. Then minus with, sorry. Next force is K2, the force from the spring K2, which is K2L theta is the force. Okay. So the force from K2 also moving upwards. From the pivot point, this will be anti-clockwise. Okay. So anti-clockwise will also be negative since we define clockwise is positive. So K2, the force K2L theta. Okay, moment is force times distance. The distance of K2 from the from pivot point is L. So you have to multiply again by L. Then you solve all of this. Okay, yeah, the class is nearly finished. So I'm gonna speed this up. I'm gonna send the full solution inside the channel. So you solve this, and in the end, you'll get your answer to be J naught theta double dot plus KT plus K1A square plus K2L square theta equals to 0. Okay, why do I do this? Because I want to make it to be like this. EOM needs to be equal to 0. Okay, so I bring everything to the left side now. So now I already got my answer in terms of UM. No, not yet. It is still not in terms of UM because your theta double dot have J naught in front of it. So you have to multiply everything by J naught, and you'll get your answer now. Okay, and you'll get it to be like this, and this is the answer for your EOM. Okay, and then for omega n square, I don't think I'll be able to solve it right now, but you can see it inside the module later on when I send the full solution. And please do ask if you don't understand whatever's happening inside the module, the full solution. If you don't understand, you can just ask. All right, so I have to finish the class now. Sorry for the rushing. So do you guys have anything that you guys want to ask, or else that's all for today?
Sir, I have a question
Yeah, yes, you can ask.
about the equation.
EOM, is it?
Yes, why
Okay.
negative kt theta is only dozen times with the distance?
Because there's nothing to multiply with because KT is situated at the pivot point.
So is it
The
zero?
formula for moment. No. Anything, any forces that happens at the pivot point, you don't have to multiply with the distance.
Okay, thank you, sir.
Yeah, like that. So it is not 0, but the force we still take into account that there is a force. But since it's happening at the pivot point, you just don't have to multiply with distance because there's no distance. But we still have to put the force inside the moment equation. You okay?
Yes, yes, sir.
Okay. Others? Do you guys have anything to ask?